In the name of Almighty God, I am Master Sankoshi, and today I want to talk about Petzval Lens stop analysis. This model demonstrates an integrated structural thermal optical performance or stop analysis of an optical system. The Petzval Lens tutorial is used as the basis for this model, together with a simple barrel geometry. The isothermal model performs a parametric sweep over several uniform temperature values, and the effect on the displacement fields and image quality as a function of temperature is shown here in this simulation. The other non-isothermal includes a thermo-vacuum enclosure where the exterior temperature is significantly different from the interior. The lens assembly is placed inside this enclosure and is exposed to this exterior via a pair of windows. The resulting temperature gradients and displacement fields within the optical system are shown, as well as with the effect on image quality. A structural thermal optical performance or SOP analysis is a critical multidisciplinary simulation workflow used to assess how thermal and structural loads impact the performance of optical systems. It maps thermal changes and mechanical deformations to predict optical degradation, for example, wavefront error in systems like space, telescope, LiDAR, and cameras. And what are the key components and process? The first one is structural analysis, evaluates stress, strain, and deformation from gravitational pressure and thermal loads. The next is thermal analysis, models temperature distribution change due to environmental factors such as direct sunlight or shade. The next one is optical analysis, calculates the effect of a structural deformation and refractive index change on the optical path, often using Cernic polynomials. The next is integration. Data from finite element analysis software, for example, ANSYS Mechanical Fluent, is transferred to optical design software, for example, Zemax Optic Studio, to simulate the final image quality. And what are the applications and benefits? The first one is aerospace and space, used for satellite and telescope, designed to ensure precision under extreme space environments. The next one is laser systems, essential for maintaining beam quality in high power laser manufacturing. The next one is consumer electronics, evaluates lens stacks for LiDAR or cameras in automotive applications. And the next one is optimization. Identifies critical high influence design parameters to enhance robustness, reduce weight, and minimize thermal induced distortion. And what is about stop analysis, structural thermal optical performance analysis? A structural thermal optical performance or STOP analysis is a critical design assessment for the development of optical payloads, particularly amongst high performing systems and for systems to be deployed in harsh environments. Nowhere is this more applicable than for an optical payload for space based observation. Often, this requires incredibly specialized optical equipment placed in one of the harshest environments known to humans and required to function flawlessly, or else risk an entire satellite becoming defunct. At its core, a stop analysis is an assessment of how the structural and thermal loads on an optical payload will affect the system's end performance. Ultimately, how very small deformations in the housing, lens, or mirrors of such a payload can have critical impacts on the end image produced, and in turn the overall mission success. Why do a sub-analysis? Outside of the space industry, a sub-analysis is commonly seen across everything from cell phone camera manufacturing to laser manufacturing and aerooptic work. Across all these industries, stop analysis provides stakeholders with the confidence that their optical payload is capable of withstanding and performing the operating conditions it will be exposed to in the real world. This is particularly true with the space industry, where a whole array of what if questions exist. in turn ensuring a payload is fit for purpose before launch day rolls around is of utmost importance to the overall mission and its success. Traditionally, a stop analysis can be seen as a time consuming and challenging process as it requires interdisciplinary collaboration between various subject matter experts as well as different design and simulation tools. However, with the right tools and a streamlined workflow, this process can be massively accelerated, whilst also enabling newfound optimization and design flexibility. A step analysis of a low satellite payload. With this particular step analysis example, we will explore a relatively simple payload aboard a low Earth orbit or LEO satellite. The payload itself is based on one abroad aerial TRIO cube satellite and utilizes two rectangular hyperbolic mirrors. Note the simulated payload that follow throughout this analysis is indicative only. It doesn't represent the actual specifications or performance of the aforementioned payload and satellite. The payload is designed to image in the visible spectrum and must fit within the TRIO cube satellite form factor. These design requirements are conditions that will be imposed on any optimization studies we might run during the step analysis, thus ensuring our payload conforms to the imposed mission requirements. This model demonstrates an integrated structural thermal optical performance or step analysis of an optical system. The Petzval Lens tutorial is used as the basis for this model together with a simple barrel geometry. The isothermal model performs a parametric sweep over several uniform temperature values, and the effect on the displacement fields and image quality as a function of temperature have been shown here. The other non-isothermal includes a thermo-vacuum enclosure where the exterior temperature is significantly different from the interior. The lens assembly is placed inside this enclosure and is exposed to this exterior via a pair of windows. The resulting temperature gradient and displacement fields within the optical system are shown as well as with the effect on image quality. Establishing a baseline ideal case in order to understand the optical payload performance after the step analysis, an ideal case baseline must first be established. To simulate such a cell ANSYS system toolkit has been used to simulate the low satellite and imaging payload as it passes over Perth and Sydney. For the ground target, a publicly available radiance texture map has been sourced from NASA's Earth Data database, providing nighttime radiance data for the cities and their surrounds. In this case, radiance data has been employed as it was the most readily available data type. However, temperature, emissivity, and reflectance data can also be used to define Earth texture map within SDK. To simulate the image the sensor would see in this scenario, SDK's electro-optical infrared synthetic scene generation tools is employed. This tool takes into account the spatial, spectral, optical, and radiometric properties of the sensor, target, and any atmospheric model employed to generate a physics-accurate view of what our sensor would see if it were launched tomorrow and we were to download an image from a Passover either city target. For the PERT example, we can make out a number of distinct targets within Perth and the surrounding area. This includes the infrastructure on Rottnest Island, the Swan River, and the Great Eastern Highway extending eastward from the Perth Strand. Similarly, the Sydney scenario shows the Wollongong CBD as a noticeable bright spot. the highway through the Blue Mountains and various suburbs along that line, as well as the dark area of Botany Bay. In this particular example, we have omitted an atmospheric model from the simulation, as our main interest lies in the assessing the payload performance on the provided Earth observation targets. However, SDK supports an inbuilt simple atmospheric model as well as a Motran atmospheric model as to inbuilt methods to increase simulation fidelity where needed. Crucially, we can also assess our scenario performance in a more analytical fashion via a spot size diagram. This result has been computed in ANSYS CMAX, part of the ANSYS Optics suite of software, and allows us another means to assess the payload performance. In a simplified sense, the smaller the red spots or the image blue, the more in focus we can expect our end image to be. Similarly, the less stretched or elongated the dots are, the less visual aberrations we can expect in the end image. This computed result will provide another valuable point of comparison between our ideal baseline and our upcoming stop analysis results. In this case, the attitude profile of the satellite is relatively straightforward, aligning itself with the ground target each orbital pass. However, should the satellite have multiple ground targets potentially lingering on each for various periods of time depending on user uploaded commands or the time since the last successful imaging window, then this attitude information could be similarly extracted for the subsequent analysis. In doing so, the orbital model is easily scalable and adaptable to changing mission requirements, integrating seamlessly with the subsequent analysis steps. And what about the thermal analysis? Next, the orbital position and attitude information is provided to the chosen thermal analysis software as boundary conditions. In this instance, our example stop analysis utilizes ANSYS Thermal Desktop due to its strong pairing with SDK and ability to very effectively solve transient system level thermal analysis across large system models. This is primarily facilitated by thermal desktops capabilities for mixed fidelity modeling, in which full three-dimensional meshed geometry, simplified two-dimensional shapes, and even zero-dimensional node networks can be combined within the same thermal model. This approach allows for simplification of simple geometric areas whilst retaining the required detail in area of complex or novel geometry to attain an accurate solution. Ultimately, the thermal analysis step allows us to account for the material composition and structural design of the satellite and its optical payload. The goal here is to calculate the thermal load on the payload with particular attention to periods of peak load. Time instances with either the max or mean temperature or the strongest thermal gradients will likely be when the most significant structural deformations happen. It's worth noting that these thermal analysis models both the payload and the surrounding satellite's structure. In many implementations, this may not be necessary as the payload will be mounted in a manner that effectively thermally isolated it from the remainder of the satellite. In this case, the thermal analysis could be further accelerated by simulating only the optical payload, provided the sufficient design and testing work has been done to ensure the payload can be treated as independent from the remainder of the satellite. And the chapter of structural analysis. With the thermal analysis complete, we can map the thermal results onto the structural finite element analysis mesh using ANSYS Mechanical. The structural deformation of both the overall satellite frame and crucially the mirrors in the optical payload can be computed. Often these deformations are going to be invisible to the human eyes. But even a small deformation can have a major impact on the end image quality. Beyond the static structural deformation, this step in the process can also assess any dynamic structural loads on the payload. For example, our hypothetical mission has a satellite aligning itself with a ground target each orbital pass. Suppose the satellite were achieving this alignment with a series of reaction wheels aboard the structure. The motion of these wheels during the imaging sequence is likely to induce some form of vibration or jitter on the imaging payload. Similarly, any slower frequency vibrations from satellite components, such as deployed solar panels, can add further dynamic effects to the optical payload if the optical payload is not isolated effectively from these dynamic effects. These high and low frequency oscillations can impose undesirable dynamic effects on the optical payload and in turn degrade the clarity of the image produced. Whilst this mechanical jitter is not something we have explicitly modeled in the simulation, it is possible to implement this across a range of fidelities within this stop analysis. In this simplest implementation, an approximated jitter can be imposed directly in ANSYS SDK's OIRS tools. For more complex implementations, an external reference file calculated in a tool such as ANSYS Mechanical can be provided to SDK, allowing for incredibly in-depth malware-specific jitter to be factored into the end image quality. And what about the optical analysis? Next, the analysis returns to ANSYS CMAX for the optical analysis. This process mirrors the analysis performed to derive the initial spot size diagram pre-stop analysis. However, the geometry is now updated to reflect the deformed state of the optical payload. In turn, the following spot size diagram is computed. Immediately, this presents a clear difference to the earlier diagram. Each spot has grown significantly in size from an initial average RMST root mean square spot size of approx. 1 micrometer to almost 50 micrometer in the latest analysis. This suggests the optical performance of the payload may not match initial expectations and in turn mission requirements. However, for anyone viewing these results who is not familiar with optical analysis and spot size diagrams, the computed result may be difficult to fully grasp. Thus, it's crucial that this information can also be presented in a more broadly recognizable and intuitive manner. And what about the real world performance? To visualize the newly computed optical performance, we simply need to adjust the sensor definition in our ANSYS SDK using the latest ANSYS CMAX output file. Doing so allows us to immediately visualize and assess the impact of the stop analysis on actual image quality. Below, in this simulation, the image compares the before and after stop analysis image. And what about the Petzval lens? The Petzval objective or Petzval lens is the first photographic portrait objective lens with a 160 mm focal length in the history of photography. It was developed by the Slovak mathematics professor Joseph Petzval in 1840 in Vienna, with technical advice provided by Peter Wilhelm Friedrich von Voigtlander. The Voigtlander company went on to build the first Petzval lens in 1840 on behalf of Petzval, where open it became known throughout Europe. Later, the optical instruments maker Carl Dissler in Vienna also produced the Petzval lens. The Voigtlander Petzval objective lens was revolutionary and attracted the attention of the scientific world because it was the first mathematically calculated precision objective in the history of photography. Petzval's lens established two new features. Firstly, it was faster compared to previous lenses with a maximum aperture of 1 to 3.6 in comparison to Daguerreotypes P camera lens of 1839. Petzval's design had 22 times the light gathering capacity, which for the first time enabled portraiture under favorable conditions with exposure times of less than 1 minute. Additionally, Petzval calculated for the first time the composition of the lens based on optical laws, whereas optics before had previously been ground and polished according to experience. For the calculations, eight artillery gunners and three corporals were made available to Petzval by Archduke Louis of Austria, commander of artillery, since the artillery was one of the few professions in which mathematical calculations were made. By 1845, Petzval's collaboration with Voigtlander, who held the license to produce the lenses, had become mired in disputes. Voigtlander moved production outside of Austria and therefore beyond Petzval's patent limitations. The Petzval objective was produced by Voigtlander and sold worldwide. By 1862, Voigtlander had produced 60,000 pieces. One disadvantage of Petzval's design was a sharp drop in sharpness at the edges, which was corrected in the Aplanage lens developed by Hugo Adolf Steinheil. And what about the optical design? The lens consisted of two doubled lenses with an aperture stop in between. The front lens is well corrected for spherical aberrations but introduces coma. The second doublet corrects for this, and the position of the stop corrects most of the astigmatism. However, this results in additional field curvature and vignetting. The total field of view is therefore restricted to about 30 degrees, and the f number of f divided by 3.6 was achievable, which was considerably faster than other lenses of the time. Lens revival. Between 1962 and 1972, the United States used the Petzval lens in the KH4 through KH4B cameras produced by ETEC. These cameras were part of Corona satellite program. This program was a secret photo reconnaissance satellite program meant to image the Earth's surface and targeted nations such as USSR. At the end of the program, the camera resolution was about 2 meters. In 2013, Lomography successfully launched a crowdfunding campaign at Kickstarter.com to produce a new Petzval lens in Russia for film and digital cameras. Lens Baby offers Petzval lenses for modern cameras under the Burnside and Twist name. In 2019, TLS rehoused the lomography lens for use on professional cinema cameras using the PL mount. The 58mm and 85mm versions were used in the 2023 feature film Poor Things. The Petzval telescope. A Petzval telescope is a type of refractor telescope that follows the design of the Petzval lens system. These Petzval telescopes are widely used in astrophotography due to their well-corrected optics. Unlike most refractors and reflectors, Petzval telescopes have a uniform, distortion-free image across the entire field of view. In standard refractors, the curvature of the front objective lens can cause stretched or elongated stars. This requires astronomers to use a corrective field flatteners or field flatten reducers to correct the distortion. However, with a Petzval lens design, the second lens group is used to correct for this curvature, eliminating the need for a field flatter. Many of the Petzval designed telescopes are quadruplets design containing four glass elements within the telescope. At least one of these glasses elements, typically in the front optic, is extra low dispersion glass or ED. Extra loud dispersion glass help reduce chromatic aberrations, which helps with color accuracy and image quality. Petzval telescopes are mainly marketed toward astrophotographers as the flat field and well-corrected optics make it ideal for imaging. Some Petzval telescopes include a visual back allowing for visual use. However, some designs don't include one. And what about the thermal vacuum chamber? Thermal vacuum chamber is a vacuum chamber in which the radiative thermal environment is controlled. Typically, the thermal environment is achieved by passing liquids or fluids through thermal shrouds for cold temperatures or through the applications of thermal lamps for high temperatures. Thermal vacuum chambers are frequently used for testing a spacecraft or parts, therefore under a simulated space environment. And what about the vacuum chamber? A vacuum chamber is a rigid enclosure from which air and other gases are removed by a vacuum pump. This results in a low pressure environment within the chamber, commonly referred to as a vacuum. A vacuum environment allows researchers to conduct physical experiments or to test mechanical devices which must operate in outer space, for example, or for processes such as vacuum drying or vacuum coating. Chambers are typically made of metals which may or may not shield applied external magnetic field depending on wall thickness, frequently resistivity, and permeability of the material used. Only some materials are suitable for vacuum use. Chambers often have multiple ports covered within vacuum flanges to allow instruments or windows to be installed in the walls of the chamber. In low to medium vacuum applications, these are sealed with elastomer or rings. In higher vacuum applications, the phalanges have knives edges machined onto them, which cut into a copper gasket when the flange is bolted on. A type of vacuum chamber frequently used in the field of spacecraft engineering is a thermal vacuum chamber, which provides a thermal environment representing what a spacecraft would experience in space. Vacuum chamber materials. Vacuum chambers can be constructed of many materials. Metals are arguably the most prevalent vacuum chamber materials. The strange pressure and permeability are considerations for selecting chamber materials. Common materials are such as stainless steel, aluminum, mild steel, brass, high-density ceramic glass, acrylic, hardened steel, vacuum degassing. Vacuum degassing is a process of removing gases from compounds using vacuum, which become entrapped in the mixture when mixing the components. To assure a bubble-free mold when mixing resin and silicone rubbers and a slower setting harder resins, a vacuum chamber is required. A small vacuum chamber is needed for de-airing, eliminating air bubbles for materials prior to their setting. The process is fairly straightforward. The casting or molding material is mixed according to the manufacturer's direction. And what is the process? Since the material may expand 4 to 5 times under a vacuum, the mixing container must be large enough to hold a volume of 4 to 5 times the amount of the original material that is being vacuumed to allow for the expansion. If not, it will escalate over the top of the container, requiring cleanup that can be avoided. The material container is then placed into the vacuum chamber. A vacuum pump is connected and turned on. Once the vacuum reached 29 inches at sea level of mercury, the material will begin to rise, resembling foam. When the material falls, it will plateau and stop rising. The vacuum is continued for another 2 to 3 minutes to make certain all of the air has been removed from the material. Once this interval is reached, the vacuum pump is shut off and the vacuum chamber release valve is opened to equalize air pressure. The vacuum chamber is open, the material is removed and is ready to pour into the mold. Through the maximum vacuum one can theoretically achieve at sea level is 29.921 inches of mercury Hg. This will vary significantly as altitude increases. For example, in Denver, Colorado, at 1 mile, 1.6 kilometer above sea level, it is only possible to achieve a vacuum on the mercury scale of 24.896 Hg. To keep the material air-free, it must be slowly poured in a high and narrow stream starting from the corner of the mold box or mold, letting the material flow freely into the box or mold cavity. Usually, this method will not introduce any new bubbles into the vacuum material. To ensure that the material is totally devoid of air bubbles, the entire mold box may be placed in the chamber for an additional few minutes. This will assist the material in flowing into difficult areas of the mold box. Vacuum drying. Water and other liquids may accumulate on a product during the production process. Vacuum is often employed as a process for removing bulk and absorbed water or other solvent from a product. Combined with heat, vacuum can be an effective method for drying. World's largest vacuum chamber. NASA's Space Power Facility houses the world's largest vacuum chamber. It was built in 1969 and stands 122 feet or 37-meter high and 100 feet or 30 meter in diameter, enclosing a bullet-shaped space. It was originally commissioned for nuclear electric power studies under vacuum conditions, but was later decommissioned. Recently, it was recommissioned for use in testing a spacecraft propulsion system. Recent uses include testing the airbag landing systems for the Pathfinder and the Mars exploration rovers. Spirit and Opportunity under simulated Mars atmospheric conditions. Each arm of LIGO detectors, the Livingston, Louisiana, and Hanford and Washington, is a vacuum chamber 4 kilometers 2.5 miles long, making them the longest vacuum chambers in the world. And here you can see in this component that I have a Petzval Lens stop analysis as a geometry. You see that we have a different lens and different stop and different group aperture. After that, in the materials, we have a shot in BK glass and aluminum and RTV, different type of glass. And the physical module that we have used here is geometrical optics with medium properties that we have used the boundary condition or domain selection here, and after that we specified our model input, for example temperature and refractive index of domain. The next one is material discontinuity, that raise to release and because concentration and focus on rays, we have used never. The ray properties, there is an equation here, the differentiation between q to t, and also omega based on cu. And obstructions, wall condition disappear, and primary ray condition none. And what about the stop analysis? We have aperture stop that you can see it's in the middle section. And the next physical module that we have used is solid mechanic, because we want to measure the stress as strain. And we come back to the definitions. For example, lens, prescription. You can see the global optical axes and the surfaces here. Material properties. For example, Young module, which define the hardness of material. It's 82 gigapascal, and Poisson ratio density. This is for shot NBK4 that we have used here, NBK 7 or NBK 2, 5, and etc. And for all of this material, we have defined Young module, Poisson ratio, density, thermoconductivity, refractor, and so on. And we go to the mesh. Here you can see that the mesh is free triangular, and it's based on user control mesh. And now we go to the ray trajectories, and you can see that how the ray is focused and concentrated on the end of the tail. And now you can see the stress here, and how much stress can be tolerated to the lens. And the next one is temperature. The next is displacement. This displacement and stress is side effect of using the solid mechanic physical module. And a spots diagram, can see that how a spot can be determined based on the geometrical optics. Thank you so much for watching my tutorial video until then, and also you can download Petzval Lens stop analysis from github.com/mahsa script.